Yeah, so I'm going to tell you about a project I've been working on using interferometric images of stellar surfaces to help the search for exoplanets. And so the reason for doing this is that I'm currently in an exoplanet group, and there are people here that are really concerned about the radial velocity signature of stars impacting the radial velocities of planets when they're trying to find Earth-like planets around sun-like stars, essentially. There are lots of people working on this in groups around the world with a number of different techniques of machine learning, principal component analysis, all sorts of things focused on the spectra and not necessarily looking for things that are physically tied to the actual star. So when you ask them, what is this signature that you're trying to remove, they can't always say exactly what it is on the surface of the star, what's creating that signature. So my hope is to help develop some techniques that will allow for that to be a more one-to-one correspondence between what's on the star and what's actually getting removed from the radial velocity signatures. So I'm going to tell you a little bit about a pilot study that we did that got published earlier this year on Epsilon Eridani. There will be interferometry, I promise. So the star is a K2 main sequence star, and it's known to have a planet that has about a 7-year orbit. So it's a good candidate. It's known to have lots of spots. There's evidence over the years of spot evolution and all sorts of things indicating that this is probably going to be the best option for this project because it's about 2 milliarc seconds in diameter. So known to have lots of spots and as big as you can pretty much get for this kind of star. And so we have observations from November 2020 from the Express spectrograph, which is an extreme precision radial velocity instrument at the Lowell Discovery Telescope and Lowell Observatory. We have test photometry from the space-based mission, and we also have some MERC-X interferometry. So this is the radial velocity data from 2020 from about 2 months. The test observations lasted about this long. And we actually took a look at that light curve, and the star's rotation period is about 11.4 days. So the 27-day baseline of the test satellite was perfect for getting us 2 rotations of the star. And conveniently, the sort of break in the middle from the data downlink was, didn't impact us because we basically have 11.4 days on either side of that. So we have 2 nice rotations from tests that we have some simultaneous spectroscopy for. These are just the surfaces that we inverted using light curve inversion. So we just take the light curve, reconstruct a surface that would create it. This is known to have lots of degeneracies. The spots may not be exactly in these positions, particularly if we're only using one light curve, which we are with tests. So there are some degeneracies to take into account, but it's a good start. So we compared these surfaces. These are pseudo-Mercator plots here, but we wrap it around the surface of the star here. We compare the surface to the radial velocity curve. And so what happens here is a graduate student that I've been working with here at Yale, Sam Cabot, takes the image that I give him and he breaks it down into components and then figures out, including limb darkening and all the appropriate features, what the spectra looks like at different points on the star and sort of averages them all together or weights them in an appropriate way to get one overall spectrum for the star at that point in time. He then takes the radial velocity of that, and then we compare it to the express data. So on the left is the image at particular points in time. On the right is going to be a red line that's going to be drawn on. That is the radial velocity from the surface at that point in time. And we're comparing it to the blue points, which are from the express spectrograph. And so you can see that the surface has some features that you can't really, that are difficult with this color table to resolve. But the overall large structures do match pretty well with the radial velocities that we've observed. And so we compare this to a couple other techniques. On the top, we have the light curve inversion surfaces. The blue points are, again, the express data. We compare it to two different methods, including Gaussian processes, which are a popular way to try to account for stellar activity in this community. And you can see that that disagrees with what's happening on the surface of the star in some places. But this was a really nice proof of concept that this technique would actually be able to account for the stellar activity signature in the radial velocity observations. And so this wouldn't be a talk appropriate for this meeting unless, of course, I had some interferometry. And so, of course, we have some Chara data, which, thanks to Tyler Gardner, we were able to get little snapshots of time in 2020. He was able to get us one set on 2 different nights. This is the first night. This is November 2nd. On the left is not an image, it's a spot model. So we just have the limb darkened disk and we moved a spot around to see where we had the best chi-squared. It has a better chi-squared than if the spot weren't there. And then we observed again 3 days later, and the spot appears to have moved. And this is actually consistent with previous observations suggesting the inclination, and it's also consistent with how much the star is expected to move based on the rotation periods. That's promising. And then we also compared this then to what we saw with the light curve inversion from the test data. And so on the top row is the test data with the light curve inversion, and on the bottom row is the Merck-X observation with the spot model. And so the rotation axis is there, and you can see that the spots are in about the same place. And it's even more convincing if you rotate the star, give it a position angle, which is, of course, something you can't get out of tests. So if we put these if we tilt these a little bit, you can see that the spots are, I think, convincingly at the same longitude. And if I overlay them, the gray now is the light curve inversion. And again, the orange is the spot model from the Merck-X observations. You can see that the longitudes are consistent and that the latitude is different. And that's a known problem with the light curve inversion, that we won't be able to constrain the latitude of the spot. So this was really promising. This really suggested that perhaps we can actually image the surface of a sun-like star and see the spots on it. So we moved on to, again, observe this star in 2021, throwing as many resources as we could at it and getting much more data from Chara, as well as some VLTI observations. And so the ground-based photometry isn't as great as the test observations, and I'm still waiting on a data set from a collaborator, but hopefully we'll get that soon. Again, we have Express observations on the top panels, the RV from Express, and on the bottom, I recently found out that Maroon X conveniently also observed Epsilon Eridani, so I was able to get that RV curve from them as well. And so we have decent phase coverage. Our Chara observations happen between about, on here, the JD, between like 20 and 30. So we have decent phase coverage in the radial velocities. Now, what I'm going to show you is a very preliminary image. Very preliminary. We have a lot of work to do to verify this, but this is an observation, or this is an image from Surfing, which John Monnier wrote. And it's suggestive that there is this one sort of mid-latitude spot, low latitude spot, I guess, because it's around the equator, and maybe some other features. We're also comparing this to Road IR, which is from Arturo Martinez and Fabian Barón. We're working to see, to understand how to use that code properly. And we're working to compare these, and we're testing some things out. So this figure may change in the near future, but just to give you an idea that maybe we are actually seeing a spot resolved on the surface of a sun-like star for the first time, which is very exciting to me. So the next steps for this is to finalize that image, obviously. And then we're going to take the image, and I'm going to go to the graduate student Sam Cabot again, and we're going to break down the surface to model the radial velocity at different points, and then compare that to the radial velocities from Express and Maroon X. And the hope then is that we can remove the signature of the star and see if there's any residual left. And we're not necessarily expecting to see the signature of a short-term planet. But now that we have the data from 2020 as well as the data from 2021, removing the signature of the surface, we should be able to see the signs of that 7.4-year orbital period of the known planet. And so we should be able, over that year-long timescale, to see some indication that there's some offset there present. So we're hoping to be able to prove that, if you get rid of the signature of the star, you can actually recover these things. So the hope is to do this to some more targets. I hope to get a couple of them this fall. Tess is going to be conveniently staring at some of my targets, so hopefully we can get that all set up and my proposals will be accepted. And so since I can't, since there's so much, since I can't not show pictures of stars, I just wanted to also show that we are making progress with the road IR code. I just briefly wanted to show you that John and I also have gotten recent images of Sigma Gem, which is a giant star, so it's not sun-like, but we do have these beautiful images. And so this is the road IR image of Sigma Gem, and it's consistent with the surfing one. I just wanted to share it because it's exciting and new, and this is another cool project that I'm working on that has simultaneous Zeeman Doppler imaging, so hopefully we'll be able to really trace where the magnetic fields are. And so I was just excited about this, so I had to also share it. And that's all I have for today, so thank you so much for listening.
Thank you, Rachel. Always nice to see an image of stellar surface. So always crazy. You have question for Rachel? Yes, please.
Hi, Rachel. This is Gail Schaefer. I just had a quick question. So for your most recent images of Epsilon Eridani, have you also tried the comparing the surfing image with the simple models of the star spots that you did for the snapshot imaging?
Yeah, I've been trying to do that, but I was using a model that didn't have limb darkening in it, and I think that was causing problems to locating where the spot might be. So I want to add that in, and I just ran out of time. And there's also the fact that John and I have realized that our observations from Merc X, we don't cover that spot very well. And so we also have Pioneer data that needs to be added into this that has better phase coverage at that point in time. So hopefully, putting all these things together, I will be able to compare this image with the spot modeling just for further verification.
Hi, I'm Fernando Cruz from Concolly Observatory. I was wondering if you have checked the inclination that you got from your fitting with the two circumstellar disks that EPS has. Do you have any?
Yeah, yes, EPS Eridani has disks that are well observed and known inclinations that are very different actually from the inclination here. We actually, for the spot modeling, used an inclination from a paper by Matt Guiger in 2016, where he used spectra and spot modeling to sort of constrain that. And he got an inclination of 70 degrees, which is discrepant with the disks. So that's, so I think so far we've only assumed that that's the inclination of the star, but that's something that we need to explore as well. As maybe it's not that, and then yeah, that's still something that we need to look into, and we know that it's a problem that they aren't aligned, and if they aren't aligned, what can we say about that?
Another question? Yep.
Hi, thanks for the nice talk. This is Nolan Matthews from the Institute of Physics of Nice. So I was just curious if there's any hope to image the appearance or disappearance of star spots, then confirm that with photometry.
You would need a lot of data to do it. You need a long baseline. I was actually sort of expecting to see the spots disappear on Epsilon Eridani because the TESS observation showed rapid evolution. But based on the radial velocity curve that we have, the spot seems to be pretty consistent over the rotation we observed and the previous rotation. So hopefully we don't see, hopefully we don't see too much evolution on this for the purposes of imaging, because it makes for more robust imaging. But I think if you observe a star that is known to be evolving consistently, you will be able to see the spots changing. But it's going to require a lot of data. And we already, combine observations from multiple nights to try to get these images. So if you're combining less data, that, it's going to be harder to see, but I think it's possible. I just sort of hope that the stars I'm looking at aren't doing it too actively.
Thank you. So let's Rachel, thank you, Rachel, again.